Great. So the title is Earth System Model Physics Ensembles. I'll explain what that means here in a moment. And I want to, because I'm an atmospheric, I do atmospheric development, atmospheric model development. So all of my results are going to be centered on that. But please, as I go along, try to maybe envision generalization to models, and we can discuss that as part of discussion topics in the last when I conclude. I not want to acknowledge a number of my collaborators here at GIS, Marcus and Anne, and Greg Sassana, Gavin, the whole GIS group, and many others spanning GIS in Columbia. So Kara told me I wasn't quite familiar with this panel, but Kara, and then I've now seen the list of attendees. I'm pretty sure many are aware of what an Earth system model is, so I can skip a lot of like, here's what a model is. And so then if we go into that model and we think what's in the atmosphere, it might look like sort of the features that we see in the atmosphere might be schematically represented by this top right schematic from Catherine Rio's paper in 2019. And so if you imagine that to be a cell in an Earth system model atmosphere, you have all of these different clouds you have to represent. Anything ranging from deep thunderstorms to stratocumulus that span quite a bit of aerial coverage, particularly in the tropics. And then all of these interact with the radiation coming in. And so you have to kind of, of course, represent all of these fairly well to get the interaction with radiation and then the slow trend in the climate system. And getting these right, is important for cloud feedback. So now what I want to then introduce the concept. So you have a model, you have equations and parameterizations. What is a perturbed physics ensemble? And I'm sure some are aware of this, and others might be less familiar with the term. So you can survey all of the parameterizations. Again, this is just the atmospheric example, but imagine this in the land or ocean or whatever. And you can survey those parameterizations representing the various processes. So something that like might represent these thunderstorm core or these stratocumulus thickness and tops, different equations, and you find all the equations and you use to describe these processes, and you want to perturb their parameters, so their coefficients and constants simultaneously. Which parameters? Well, not ones that might relate to Coriolis or or gravitational constant, but maybe something that relates to thunderstorm vigor. So something not, coefficients as part of equations that are not, where the equations are not, easily derived from first order principles. So it could be an equation related to thunderstorm vigor, like how we see right here. It could be something related to microphysics, where you have these coefficients that map the role of cloud water and rainwater to how the evolution of those two things change in the future at the next time step. And then you have other, recognizing the current state of modeling, you have equations not in the traditional sense, so I'm sure showing up here, but like you have a neural network mapping some sort of set of inputs to outputs, and hundreds more. And so the idea then is that you can collect all of these equations, and you look at the coefficients in green. That means they're perturbable. Red, not perturbable. Gravity, no, we know that. And so you can store all those parameters in a vector, and then randomly perturb them, and then run the model, and you get like an output, and you have many outputs. Here's an example of precipitation, but you can get different radiation outputs, whatever. The list is limitless. And so you can then compare any one of those ensemble member outlooks to observations for its respective variable, like in this case, series radiation. So you can compare the model radiation to series, and you can say, oh my gosh, like for this particular random parameter configuration, the radiation looks nothing like Earth in this top, where you see biases on the order of 50 watts per meter squared. Like, yikes, okay, not a good configuration. The bottom is an example, and you might have hundreds of one where the radiation differences are smaller, and it, okay, maybe looks somewhat like Earth. It is often the case that when you come up with a typical set of parameter configurations and run the model forward, most of the model members do not look like Earth in a typical PPE. And so this is visualized with one particular variable. I'm showing a histogram of absorbed shortwave radiation from the ensemble and at the top of the atmosphere over this multi-hundred member ensemble. And you see that the distribution, by and large, does not overlap with the observations, or a few members agree with the observations, which might fall within this vertically thin blue partially transparent box. And then you can also know in your head that if you were to look at other outputs, say precipitation or water vapor, even though you might have some members that have similar radiation in this multidimensional output state space, those other members likely will not look like the observations. So it is very unlikely that you can come up with a PPE in some sort of randomly perturbed way where any member agrees with the observation. So by and large, PPEs, as we typically construct them in the atmosphere, most members are not Earth-like in some way. And there's an implication for this, and that is physics parameter and output relationships, commonly shown in many PPE atmosphere analyses papers, includes many members with sensitivities that are not characteristic of Earth. And I think that's a problem. And I would argue that we should really be thinking about sensitivities, so how outputs connect to parameters under some constraints where basic fields meet basic Earth observations. So where, for instance, one member is not 15 watts per meter squared out of TOA radiative balance, or has a rainfall or precipitation globally of 5 millimeters per day or 0. So we should come up with new ways to compute PPEs in general. And so what I am advocating is more focus on constrained perturbed physics ensembles with some of these requirements. So a minimum requirement would be to find all combinations of parameters that was in that P experiment vector that yield model output that is in agreement with base state climate. And what is the base state climate? And this is an important detail for some of the later points I discuss. A base state climate is has all of the something beyond just radiation, water vapor and precipitation. It has some other like key things we observe. Maybe low cloud fraction split into its stratiform and shallow cumulus components, or maybe warm rain fraction on Earth. So something that like truly we're sort of maximizing and acknowledging that there are many observations available, and we should use the products to the extent possible. Now, as one envisions using new observations, we also have to be aware that some of these cutting edge but valuable observations might have more errors associated with them. And so some of our attempt to get a more comprehensive base state with these observations, I think, requires closer model observational interaction. And I hope to demonstrate this is going to be important for quantitatively assessing the value of process scale observations and constraining the predictions that we want to get from the very CPE that I'm arguing that we're creating, or the very type of constrained parameter ensemble. So a final question that we have is, what are the observations at present? Why do I bring this up? Because it might be that the uncertainties that we have in the observations, especially as models are improving, they might matter for judgment on what's a good model and what's not. And it's possible that this actually has maps our definition of good or not to projection. And so we really should, especially as both models and observations are improving and rapidly expanding, we should start thinking about, does it matter? Are observations really truthful, or are there errors in the observational products we use, and how do they affect our interpretation of the goodness of a model? So some of these aspects we include in this definition of a PPE called a calibrated physics ensemble, or CPE, which came out in a paper here in James earlier this year. And so the workflow to get to a CPE goes as follows. You start with your random perturbations of parameters, and then you create your PPE, the typical one, the one I said has some limitations. And then you quantify, using all your PPE members, the state space of the errors associated with each parameter combination. So that's denoted by these asterisks. So one asterisk will have one parameter vector, another one will have a different one, and they'll all be different. And then the climate error, this is really like you can't show this easily in two-dimensional or three-dimensional space here for a schematic, but this error is sort of like a vector, or it could be a bulk error. And so the idea is for every parameter combination, and again, there'll be like 50 parameters, 100 parameters, you get some estimate of its net error in the climate sense. And that's all represented with these asterisks. Now, we're missing a lot of state space because you can't sample everything. So to fill in the gaps, we use machine learning, and this could one can use different types of architectures. In this case, for what I'll be presenting here, we use a neural net to sort of map all of the empty space and fully fill out the state space, so we can quantitatively say how parameter combinations map to a climate error. And so then the idea is, once you go through this process, you invert the problem, and you can find all of the good parameter combinations that minimize this climate error in a multidimensional state space. And that becomes your collection of ensemble members that go into a CPE, which is different from the PPE. So some key aspects of this are taking into account the observational, possibly the observational error in this error diagnostics that we compute. So we have the paper describes this in detail, and I won't go into the details, but this whole the whole quantification of the error it does account for errors in the observations, and it has the power or the ability to change the errors, the climate computed errors, quite readily across the ensemble, and that's an important thing, which I'll go into here a little bit later. And again, this is not just one error; it's really many across many diagnostics, or in any model configuration you're doing the land or ocean. You have your own set of parameters and your own set of observations you use. What I'm arguing here is that the way we compute error here is takes into account observational error. So at the end of the day, you collect all of your your well-performing model members that where your climate error is minimized, and the idea is you store them in what we're calling a calibrated physics ensemble, or CPE. And so by definition, calibrated in this context means that all model outputs look closer to targeted observations by design. And so here's an example of how this might look. Let's say this is a really good performing model configuration, as is down here. You take those, okay, this is really just two parameters, but you can imagine this is in a 50-dimensional state space. In this case, we have for parameter 2, it's sort of high, while parameter 1 is low. In this situation, we have the opposing, the contrasting example of this setting is high, but for 2, it's low. And so by definition, both of these give us good results for the observed period where we have observations in the present day, but there's no guarantee that you have similar performing models in present day and they have a same projection. And so more likely than not, you probably have this situation where you have divergent projections, and that's because perturbing parameters, specifically ones that when you're perturbing a lot, those connected processes, and the processes are probably really important for prediction as opposed to just mean state fidelity. So you collect all of these in this high dimensional state space, and you can end up and build with projections, right? So a CPE enables us to not just look at how parameters connect to outputs under the constraint that all of these states that we choose, all of the members, look Earth-like. We also can get a nice way to quantify uncertainty in the various predictions that you might have. So what advances might this type of ensemble enable? And I sort of arrived at four themes, 4 points, all of which we're sort of working on at present. One, where are the biggest structural errors in a model? By structural error, I mean a bad equation. So we tend to think that if we're deficient in, say, stratocumulus clouds, we might have bad physics for the stratocumulus clouds, and we'll never get them good, while also matching radiation. But maybe the collection of all of the various tens of coefficients we have in our existing equations, maybe they're bad. There's a lot of parameter interactions. And so maybe what we think is a structural error could be parametric. And so this process of constructing such an ensemble enables us to tackle this question, I think, more robustly. So secondly, how do errors in the observational products, which I was discussing about before, impact predictions? By incorporating observational error into this whole process and whole workflow, we can then, when we pick our ensemble members that are good, or since our judgment of good is based on observational error, then we know that our selection of CPE members is conditioned on observational error, and therefore, since each CPE members maps to a prediction, we can shape or craft the ultimate prediction envelope that comes out. Thirdly, this whole type of PPE enables I think, a bridge for understanding the extent to which models disagree due to insufficient exploration of their already included physics. And I'll give examples for each of these. And then an exciting advancement is we can use a CPE to sort of establish the value of new observations in constraining model physics, which is pretty exciting, and it's complementary to the traditional that many might be aware of, observing system simulation experiments that are focused on understanding constraint in the initial state uncertainty. So this is constraint in physics as opposed to constraint in initial state uncertainty that is used to drive models. So let's talk about this question first, assessing structural errors using a CPE approach. So what's structural and what's not? So when I'm going to give an example here. Our PPE, again, that's the ensemble that's not constrained, random perturbations of parameters. That's denoted by all of these black dots. And what I'm showing here in the top left is again, we have many outputs, but I'm showing the joint occurrence of each member's OLR with shortwave radiation. And it spans this space. And here the crosshairs denote where the observations approximately lie. And so in the process of trying, you see many members, as I hopefully convincingly argued for early on, many members do not look like the observations. The CPE is sort of this final collection of green dots. These different colored dots denote different iterations in creating a CPE that are used in the process. I won't go into the details on why we do that, but at the end of the day, a CPE will be centered near the crosshairs of any observations. Again, this is in a multidimensional observational state space, so you know that if you're matching these observations, you're also matching the other variables as well simultaneously, like cloud variables, precipitation, and whatnot. But again, many variables, many configurations are not Earth-like. So here's an example. We have long thought in the GISS model that we did not have the physics for stratocumulus. We were always deficient in shortwave radiation off the coast of the continents. When we would improve things, we would do it at the expense of other features, and we could never simultaneously match radiation and stratocumulus. And so this process and getting us closer, when we look at the various iterations of CPEs, we actually found that we could approach the targeted, the crosshairs of where the observations lie for the joint occurrence of shortwave radiation in terms of cloud. This is actually cloud radiated forcing and stratocumulus cloud fraction that was not evident from the PPE. So the act of trying to fit a surrogate model to map the space between all the parameter combinations and the outputs, and then inverting that to find all of the good combinations, actually gave us a mode, a number of modes where it says, oh, hey, guess what? You actually might be okay. You might have the physics. You just have seriously bad sets of parameter combinations. And so maybe we're not as structurally deficient in stratocumulus as we previously thought. Here's a contrasting example. So it's like, okay, so one thing we know is that we suspect that we do not make mesoscale convective systems, which are those 100-kilometer scale rain-producing systems in the tropics, and we suspect that we do not produce their rainfall characteristics very well, mostly due to lack of physics, so lack of actual equations, not a parametric problem, but lack of actual equations. And so when we run the PPE and we look at the outputs, indeed, we never can get up here where the crosshairs might be associated with that. When we do in the construction of the CPE, we see it never budges us any closer to this crosshair as well. Although one could argue, oh, but you do have some members. Well, here's a member. Maybe this looked okay. Well, it turns out, as I had said before, well, yeah, that looks okay in this space, right? But it looks terrible in the shortwave radiation space. So that's because even when you have PPE members near these observational crosshairs, for particularly displayed observations, in this case, long wave and stratiform rain, you're deficient in other aspects. Whereas in the CPE creation, you know that when you agree with the observations for two things shown, you're more likely to also agree in other observations you're not showing. So it's sort of a multidimensional, it's hard to display all this in multiple dimensions, but that's the difference between CPE and PPE. And it does help us to disentangle this problem of understanding where are we really deficient and where are we just massively under exploring the existing physics we have in a model. So the second advancement, how do errors in observational products impact predictions? So recall this slide I showed earlier. And I tried to explain that this climate error we compute, which is basically, there's flexibility in how one computes this. This could be simply zonal mean skill scores across all of the observations. Okay, so you take each PP member and you score it against zonally against water vapor, cloud fraction, radiation variables, whatever. But if we take into account the observations in those, the error in the observations, this whole computation of the error would change. And so you can imagine then if we redo this with observational error incorporated and we rederive the histograms of good parameters, we might have a fingerprint or an impact on the final distribution of projections. So how much progress have we made here? Well, when we included observational product discrepancy in the estimation of the good combinations of physics parameters, we find that they're very different. Somewhat surprisingly, when we assume no errors in the observations, so we really do think they're observations and not retrieval products, versus specifying errors in the observations, you can see how for this one parameter, this is an entrainment rate for convection, which many on the call know that convection and entrainment that you assume is a very key climate model parameter that's often perturbed or tuned. You can see that the distribution of the good settings across the CPE is different if we assume errors in the observations or not. Here's an example for icefall speed. You can see when we incorporated error into the computation of climate error or incorporated observational error, we have this distribution shown in the yellow. And when we did not assume error, we had this bimodal distribution. And so this is as far as we've gotten on this. We already know that some of these different members have different ECSs. And so in this way, we have a quantitative mapping between observational error, product error, that then gives you an error that goes or gives you a direction that helps you constrain the histograms of parameters, which then maps to distribution of predictions. So this is something you can't do from a straight PPE. You need sort of a constraint ensemble approach. Another advance is CPE.
Can I ask a quick question? Sorry
Yeah.
to
Yeah.
interrupt. It's
Yep.
Alex Gonzalez.
Hi, Alex.
Hey, Greg. Can you clarify, are these atmosphere-only simulations?
Yes, these are atmosphere-only simulations at present, yes.
Okay.
Well,
So
I'm
guess
sorry.
you're getting ECS.
Actually, this is not true. I'm falsely saying. So what we did here was we took, so everything was done in atmospheric mode, but what this is actually work with Greg Sassana. What he did was he took a few of these different, so we have like 100, these histograms represent 100 members. He took like a handful, like 10 of them, and ran them through in more like coupled mode. And that's how we got that. We just didn't run the full histograms through yet. Does that make sense?
Yeah, that makes sense.
Yeah, thanks. Okay, so a third advancement, CPEs and models, I think, enable us to have a bridge for understanding the extent to which models disagree due to insufficient exploration of their already included physics. And I'll give you an example. So this is a paper in the bottom right from Jonathan Zhang back in 2021. And they were computing their, for all of the different CMIP models, they were computing some sort of bulk performance score for all ESMs. And they did this for CMIP 6 and CMIP 5. And then they plotted this against their ECS for each respective model. And so you see some relationship between the score that exists for CMIP 5, and then it's different for CMIP 6. And it's really hard to understand why different models disagree with each other, not to mention the fact that they disagree even in a different way over different CMIP iterations, without having some knowledge of the underlying model state space that could be inferred by doing a CPE approach for every model. So what I'm arguing is that CPE type efforts per institute allows us to allows us to see where overlap exists. Because you can imagine for each model here, you could have some sort of um, bars that denote its range in ECS. It might be huge, might be small, or any other projection metric. And you can start seeing where the overlap exists and where sensitivities are similar, particularly in light of these sort of situations where we have differences in models um, in terms of their projections. Those differences change as a function of the CMIP iteration. Mark's Linkous showed something similar as well in the bottom left when he was looking at higher latitude feedbacks and for cloud feedbacks across the CMIP generations. And so I would argue that if we focus more on models in general producing as they're released, coming up with some sort of way to orthogonally or sample orthogonal vectors in their viable parameter state space to see the impact on projections, it will help us to understand why we differ and if our sensitivities are similar, if we have similarly constrained physics parameters, particularly since a lot of us share a lot of the similar schemes for many cloud processes. And again, just imagine this idea being expanded to some other component in a model, whether it's land or ocean representation or whatever. And so finally, another nice advancement is the value of new observations in constraining model physics. And this is complementary, as I said, to the traditional OSCEs that are focused on understanding constraint in the initial state. Um, and so this is a paper that was just accepted recently, probably a couple of weeks ago. It's in BAMS, and the schematic is this. So we use the current observations. This is the very expanded. What I argue is you have to get really good on defining the base state and using the observations as much as possible to give you what I would call a baseline selection of physics parameters that are then used in all of the schemes in your individual model. Each of those has can be run to give you a CPE member, and then you can get the range of predictions. Now, that's the existing workflow that I sort of have already described, but we've learned, especially with the advancements in AI, that we can actually, look at the climate error in a way that involves the use of like hypothetical observations. So for instance, we've already learned that we can emulate the model behavior for column water vapor, ice water path, surface wind. That's how we fill in all the empty space between the actual samples we took and how we can find where good parts of the state space are. Let's say we want to emulate other things. So let's say, well, we don't have good planetary boundular observations, but let's pretend we did. Or perhaps we're using some sort of process level observations that might relate to vertical velocity and thunderstorm cores as a function of their ecotop height. Let's say we had these sort of globally, or we had them in limited regions. And so when we're constructing our PPE, our non-constrained ensemble, let's output some of the diagnostics that might be related to such metrics, and then go in and say, you know what, let's pretend we have an observation of it, whatever you think it might look like, and then run this whole framework forward. So you put in a fake observation and a fake uncertainty, and you can see if you run this fully through the whole workflow and run in coupled mode, you can fully see the impact on the heat waves, ECS, frost, whatever. So this whole CPE approach allows you to put in new, not yet observed observations, and then find the modified but still good parts of the state space, and then see the impact on projection. You might learn what has a lot of bang for its buck and what does not in terms of affecting your projections. And so we did a little of this we did an actual proof of concept on this in using water vapor and temperature at 925 hectopascals, where we're showing the changing distributions for different parameters. We have about 50 parameters, but the blue shows how parameters are changed when we do this sort of process, and the yellow is sort of before, and you can see, or I might have that reversed. And the idea is that, okay, if we just pretend we have water vapor at 925 hectopascals and we change the uncertainty on it, or we reduce it, you can see different impacts on parameters, right? And that's what we show here, but not every parameter. right? So for instance, we see no impact on fall speed of snow, no impact on on how quickly cloud ice converts to precipitating ice. These are mostly parameters related to convection and how often and how quickly shallow clouds decay. So in our proof of concept in inputting fake but really reliable 925 hectopascal moisture, we can see to what extent our parameter histograms change. And then we can map that fully through to see the impact on the cloud feedback and by extension ECS. And this is again following on Alex's question. This was had to be done with more not atmosphere only model runs, but you see where we did this sort of approach and we arrived at different feedbacks. And so this is a quantitative way to say, how does the value of a new observation change your distribution of feedbacks? And if every modeling center would hypothetically do this, and many of them sort of agreed that this was a good idea to do in our BAMS paper, then you could collectively all establish the value of new observations on physics parameter settings. And hopefully this is obvious how this is different than the use of observations to constrain the initial state in a model, such as like, SST or water vapor, things that you do with traditional OSSIs and NWP in particular. And so I'll just conclude with these same bullet points that I already have. Went through one by one. These are the papers that we have all from this year that are related to these ideas. I won't go through these points, but maybe I'll just leave the slide up because then we can discuss these and anything else that might come up. And with that, I'll end. Thanks.
Sure, but I have a lot of questions and I put them in as I go. So I think, yeah, maybe I'll ask one question and then let other people speak. I guess perhaps my last one, which is more of a general question, and that I think fits really well with the questions for our panel, is to say, like, I really appreciated your last point, thinking about looking at basically how well constrained other parameters versus, the value of adding additional observations. And I was just trying to think, could you see that being extended to say, having a similar approach to test whether new processes or new parameterizations have value?
Yeah, I do. So that's great you bring it up. We had this discussion with the group, I think just last week, and because probably related to that is I don't know how many on here who have developed parameterizations and put them in a model, and you have the darndest time trying to get the model, like it didn't behave as you thought, or the behavior is different. So if you sort of like did a simultaneous perturbation of everything as you put in new parameterizations, so because you would definitely want to, like, if you put in something new, you want to, like, acknowledge the fact that previous settings for all of the other 10 schemes in there might have been optimized to work with that existing scheme that you just replaced with a better scheme.
Yeah,
if
for
you do
sure.
this whole
That you've
process,
overfitted your other parameters.
exactly, yeah,
Yeah.
yeah. So I think it's definitely, I think it would definitely be worth doing both simultaneously. Yeah. And just swapping. But I think you have to, you probably, I think you have to, because of what you just said, I think you'd have to still, when you put in the new parameterization, you probably should right off the bat try to compute like a constraint ensemble.
Yeah, but you would still need a full implementation, and then that's used as in a way to evaluate or tune the other parameters? Or is
Yeah,
that
well,
something that,
you just
yeah.
the way I would envision doing it is sort of like, okay, I mean, and we're doing this right now with we're doing aspects of this right now. So put in the new scheme, and that new scheme might have so you have the model as is. You do a calibrated physics ensemble. You look at the distribution of whatever projection metrics you're interested in. Okay, and then that's your baseline, and then you go back in, and you swap out the parameterization, and then you redo the whole process, but with that new parameterization in, and then you look at the distribution of outputs, and you compare the two. I think it would be a false. I think it would be you might risk you might think that your parameterization doesn't perform as well if you sort of separate it from redoing the whole CPU with the new parameterization in. But I think you would need to do like a baseline constraint ensemble and then a new one with all of the parameters re-optimized, I think.
Okay, thanks for your thoughts on that.
All right, next we have Alex.
Thanks, Greg. That was really informative. I have to admit, I tried reading the paper and feel like it's better to see it always in presentation form. And so I feel like one question I had, and you sort of addressed it, was this idea of like the uncertainty in the observations. So for example, if we're thinking about convection, like a lot of the satellite retrievals depend on these field campaign observations, and those are only certain regions or limited regions. Some regions have been underexplored, and so this is maybe not even a question that I expect to have answered, but the uncertainty, the level of uncertainty, is a global sort of net uncertainty, right? Doesn't have any spatial pattern or anything like that, or regionality to it, correct?
Well, it does, but I guess you could say the question is like, what do people report? They might report a global uncertainty, but that could be due to the difficulty in really getting a robust uncertainty estimate, but I wouldn't argue that's correct.
Yeah, and I guess following up on that question, if you don't mind, just like the joint space between, for example, low clouds and convection, and there's some overlap, obviously, and places where they don't overlap in the parameterization space. But for example, showing that the models are, the parameterization is actually, it can potentially get stratocumulus clouds more accurately. But it looked like for like deeper convection and stratiform MCS, they're just out of range. And so I guess, are you guys mapping like joint spaces?
Yeah, we try to. I mean, it's hard to try to come up with nice ways to visualize it. But yeah, we're trying to come up with, we're trying to define and quantify these discrepancies in a high dimensional state space, to really assess, okay, is there a structural error or not? Like for instance, you might, if you just sort of project it to a two-dimensional space, it looks like you're mapping, you can match two things, but then you're way off in something else. So that's a structural error, right? So how to nicely display that is difficult. But yes, we're working on that.
Thank you. Thanks.
All right, up next is Ming.
Okay, can you hear me? Hello?
Yep.
Yeah.
The first question is, you mentioned you did some, you pick up some perturbation configuration and run some couple simulation. Do you usually retune the model? Since if the two-way radiation is off much, usually it's pretty difficult to study in the couple framework.
No, because so in the creation of the atmosphere only ones, by design, one of our the CPE members all have TOA radiation that is in near balance. So then when we run in coupled mode, it starts out as slightly out of balance. But our experience has been, if we start with members in the atmosphere only that were not 10, 20 watts per meter squared out of balance, and we're only by construction, if we're only a few watts per meter squared out, we've had success in running arriving back at balance pretty quickly with and the process of doing so didn't really mess up some of the other good features in the atmosphere only runs. What has been difficult though has been trying to there's subtle nuances about, like, so for instance, you can have good atmospheric radiative balance in the global sense, maybe in the zonal average sense, as you might expect, but then there might be like a really odd an anomaly, say over the North Atlantic, that the ocean model doesn't handle very well, and so you end up with a lot of cooling, and then it affects the AMOP and all that. So there's some pathologies to and you can imagine incorporating that in the development of your own calibrated physics ensemble. But I would say that's like that the whole extension to couple models and how to accelerate their development using in this sort of way, I think is it's pretty active area of research.
Mhm. The 2A net radiation is one of the important variable you try to optimize closely enough
Yeah,
to the observation. I see.
right.
Not so much on also the individual component, the long wave and short wave component. Each will also
Individual, yep,
be okay.
both. Yeah,
Yeah.
definitely not like imbalance, but what yeah, that's right. By
Mhm.
definition, it would be imbalanced, but also not not something that's like 220 watts per meter squared for both.
Mhm.
Closer to 240. Yeah.
In one of your figure, you mentioned the stratiform fraction. What's your definition of that? Do you just use the stratiform, any precipitation come from the stratiform module, or you have some specific sort of detection? Because in the model, the stratiform is quite, it can be quite arbitrary.
Yeah. So in our case,
Mhm.
when we were looking at, we made a diligent effort to try to know what fraction of the stratiform was, like we have information at the subgrid scale that we use. What part of it was driven by frontal systems, like synoptic scale stratiform, and what
Mhm.
part was sort of the convectively driven stratiform anvil.
So,
And
you,
so I mostly focus on the latter.
so you don't, in the typical precipitation, only two module or two parameterization produce precipitation. One is convection parameterization. The other is sometimes we call stratiform or large scale or resolve scale,
Right.
whatever you call. That's quite often, the ratio between these two. Sometimes we also call that fractional, uh, the fraction of precipitation that come from large scale module.
Yeah.
So that's actually quite arbitrary as you move, for example, change model resolution or change convection scheme. You always see this fraction can change quite dramatically. In the extreme case, if you turn off convection, deep convection parameterization, pretty much
Sure.
everything is from large scale.
Right.
So that's something,
Yeah. This.
actually it is by nature, it is convection, right? If you turn off parameterized convection, everything looks like large scale, but in fact, it is convection. So that's,
Yeah.
I
Absolutely.
kind of
So
worry about the model and observational comparison of that can be,
yeah, I mean
yeah.
that's mostly a pet project of mine because I'm a convection person by background. So I
Mhm,
kind of knew what to do in our model, and this is our own models, and I'm a developer, so I
mhm,
kind of knew. I would not advocate, and this is the feature. This is what you're referring to. Um,
mhm,
I this brings up a topic I didn't have time to go into, and that is apples to apples comparison of your diagnostics with the observational equivalent, right? I
mhm,
designed this to be what I knew I was getting from GPM for stratiform associated with convection. Other models might not have the capability. If you don't have the capability, then you can't look at your output in this state space. We can, because I coded it up to try to be as faithful as possible between these two representations, these two distinctions of rainfall. And we did the same thing for stratocumulus cloud fraction as well, where most models will give you a general low cloud fraction, and we try to come up with a way that was faithful to the cloud set, maybe
mhm,
perspective on stratocumulus. So this, I didn't go into this, but one,
mhm,
if you have 30 outputs, one would have to make sure that each of those outputs you're then comparing with the observations to do this whole CP development and evaluation. You'd have to know your own model and know, like, oh, can we do this with our model? If not, that reduces your set of outputs that you can compare with the observations, right? But all of us
mhm,
share, like, there's enough. So yeah, I didn't go into that, but
mhm.
for this case, it was because I am particularly interested in improving the physics of this. So I spent a lot of time on doing this, right?
Yeah, that's great. And my last question about convection, also about this structural error. So, as you know, a lot of people criticize in-training plume model as a representation of convection. Since Kerry Manuel's paper, some earlier paper like stochastic convection scheme or the episodic mix and buoyancy sorting scheme proposed by Kerry Manuel.
Mm-hmm.
So I think that's something people always kind of worry about, what this particular structure error. Because in the real, people argue this all the time since 1970s, the entraining plume just does not like the real cumulus cloud.
Right.
Inside the cumulus cloud, you see updrafts and downdrafts. So let's say if we want to, pretty much all the current global current model use this in-training plume idea as a representation. So if we want to explore what this particular structural error, potential impact of this structural error, what would be the a good way? Like in a model that share this in-training plume, would they produce a particular future climate prediction bias towards a certain direction,
Yeah.
including
Well,
ECS or cloud feedback, something like this?
yeah.
Then even let's say you take the in-training plume, with a single in-training, some model just a single increment of weight, you cannot use that model to represent both shallow and deep. Quite often, that gives some model does not have a downdraft, for example. So if we can systematically explore, whenever we include an additional degree of freedom, like a model with downdraft, what makes that model special? Characteristically different from a model without downdraft, or crude pool representation or something like this. How
Yeah.
can we do this in a more systematic way?
Well,
That's my sort of general question.
yeah. I mean, I think it relates to the first or second question too, right? About putting in,
Yeah.
can you assess the value of the new parameterization you put in? I would advocate that that if people can, and I think we're working on progress on how to do this, but if we can come up with like general perturbed physics ensembles, that's all the black dots, without doing the new parameterization, and that might have a plume representation for convection, then do it again, but this time put in your new, maybe you have a thermal approach for some sort of rising thermals for convection, and then redo it again, and you'll have new parameters, and you'll have some of the existing parameters that were there before. Come up with a new PPE, so you have two PPEs, and then try to calibrate both and see. Like the thought would be, if you have the appropriate diagnostic relates to convection on the y-axis, and some radiation thing on the x. The thought would be in my head that you would see a slow shifting toward the crosshairs of where the diagnostic should be, as you put in the better structure, and you should see that sort of reflected in the shifting of the CPE too, right? So I think a way to understand is to start doing more. If you put in new structure, new convection, you should, before you say if it was good or not, see how the whole, run a simple PPE, maybe do a mini CP inference, and see how the whole ensemble shifts as a
Do you
way
worry
of
about the
assessing the
response,
pattern.
like response to warming or response to a particular
Yeah, well,
pattern of warming or response to greenhouse gas aerosols? So
yeah,
this
I mean,
kind
you
of
could,
response
yeah.
is really important. Yeah.
Yes,
Okay.
you could do, yeah. I mean, you could set up a whole hierarchy of, but most of what I described here, we have automated in a set of scripts, and we have ways to not not request too many computers or too many nodes for running things, because we have a way to sample. So I think the key is just, we have to, if we put a new structure, we have to still perturb everything, because it is going to be the case that more often than not, that if you put in a new structure, the model, the goodness, the improvement in the model isn't going to be realized until everything is until you come up with a new set of physics coefficients for all of the other schemes that were inappropriately calibrated to a previously bad convection scheme. And if you've improved that convection scheme, you need to reset all of the other physics coefficients. So I think the two should go hand in hand, in my opinion.
Thanks.
All right, we've got just a couple minutes left, but I'll go ahead and say, Elizabeth, what's your question?
Sumi, you can hear me? Cool.
Yep.
Thanks for the cool talk. That was really interesting. This is kind of very similar to what Alice posted in one of her comments, but you already mentioned in the ocean, things can take a lot longer to adjust. And sometimes you get bias development, like you mentioned in the North Atlantic, and then the AMOC goes off the rails. I'm curious, is anyone thinking about how to solve this question in the ocean when it's just a lot more expensive? And do you have any thoughts about how folks are trying to get around this? Because there's just as many issues with trying to find the right parameters in ocean models and fully coupled on that side.
Yeah, I guess, I've been part of a number of this, so I don't think anyone has a good answer, but I've been part of a number of discussions about what in the atmosphere is a proxy for stacking the deck in favor of that atmosphere working with a particular ocean configuration? Or is there some way you can look at the spatial structure of the surface fluxes from the atmosphere as a way to sort of select what parameters you might want to start with in the ocean? Um, I was also intrigued by recent like discussion I've had about, I'm aware the oceanographers are using surface wind convergence over the ocean a lot in some of the oceanographic studies. And we don't use that as much in the atmosphere. So I'm sometimes wondering if we looked at our surface wind divergence field over the global oceans, how would members, which obviously relates to forcing of the ocean surface, how would members that have a good, um, representation of that perform when they are used, when their atmospheres are used in coupled mode? So I feel, I feel like this is almost like the holy grail of auto calibration approach for coupled models. And as you say, the timescales are difficult to account, how to deal with that. I'm hoping that we'll make progress on diagnostics, I guess, that would serve as a proxy for behavior in the ocean. But I'm hoping that like more people will discuss this, and then I could be a benefactor in hearing good ideas.
Cool. Thank you.
Thanks.
All right, and we have time for just one more. And I see Eric, you put a question in the chat. Would you like to ask that?
Oh yeah, the hope would be that if you did this kind of thing, then you could use that to sort of design observing systems. You could
Yeah.
prioritize between, a LiDAR from space and something to do with, top of atmosphere energy balance. But that
Yeah.
would only work if all of the models agreed on which were the most important observations. And I wonder about your thoughts on how likely that is.
Yeah. So we hosted a workshop on this it's been about a year and a half, where we tried to invite some folks from different modeling groups, and I agree with you. You'd have to like, you if you do it with one model, that's good, but that's not enough, right? So um, it seemed a lot of us were in agreement on this sort of approach for using multiple models at multiple institutes. Um, and we wrote about that in this paper. But in terms of actual work having happened since then, we haven't done anything for various reasons that you can maybe imagine.
Oh yeah,
Um,
of course.
yeah, but yeah, we all like, yeah, we should really work on this, and maybe it could be part of a joint effort that instead of just all of us randomly saying, well, we think this is important, maybe we can more systematize this sort of an
Yeah.
effort. Yeah, but
I
I
know
agree with
this.
it has to be multiple modeling groups to demonstrate it's not just unique to your own model.
I mean, this thing that David Stainforth kind of mentioned a while ago, that you could get different answers just depending on how you define the parameters. I mean, if I
Yeah.
use, temperature as a parameter, I might get one answer, but if I use 1 over temperature as a parameter, then I would kind of have a completely different way of looking at the phase space. And so,
Yeah.
you could see all kinds of different ways in which the meaning of the parameters, even though physically they mean the same thing, they're written out differently, and therefore you'd have a lot of kind of challenges just kind of creating an apples to apples kind of system.
Yeah, we might. Yeah, we definitely. I know, in our discussions, we definitely were like, well, we don't want to. I mean, to be honest, a lot of us we share some. There's not complete independence among the schemes we all use. We do share a lot, but then as you point out, yes, there's some that where we have our own parameters. I don't know that we would ever, you know, try to arrive at some sort of say, okay, only use these parameters. I think we were hoping that people would use, there some selection of common parameters, but then have their own in-house that might relate to their own model. And then we demonstrate, and we can do this whole framework. You just swap in the parameter names are different in the whole beginning before you call the scripts and do all the work. And then we can sort of collectively see the role of the observations on our individual model. If anything, if we actually saw similar importance, even though we have different parameters, similar importance of an observation, that would be pretty cool. But Yeah, work to be determined. I'm trying to get away from just, I'm advocating that we need to move on beyond saying this will, these observations will improve models. Okay, let's systematize that and add some
Right.
on that general statement and proposals.
Yeah. Okay. Thanks.